In this lecture, we will be discussing two applications of monotone convergence theorem. First application is where we will be finding uh, inductively a square root of any positive number, and in the second number, we will be establishing the existence of an irrational number. We will be just establishing a number between 2 and 3. I'm not going to prove that that's a irrational numbers, but that's an important irrational number. E lies between 2 and 3, and that is important second to pi. So first, let us establish through this example that we can construct a sequence inductively, and that sequence will converge to the square root of a positive real number. Let us take a to be a positive real number. Let a be a positive real number, and I have to construct a sequence which converges to the square root of this number. How we are going to construct this sequence? This is to be noted here. I'm just starting with an arbitrary real number s1, and s1 be the first term of such a sequence which is expected to be constructed. And I am not taking any particular, it doesn't depend upon a, it is not defined with reference to a, it not taken with reference, it's just an arbitrary positive real number. And then by using this real number, we are constructing a sequence through this induction relation, this recurrence relation. The n plus 1th term is defined to be 1/2 of the sum of nth term plus a upon nth term of the sequences. And then what we are going to now next establish, that this sequence so defined, starting with an arbitrary positive real number, is a monotone sequence. It is a bounded sequence also, and then monotone convergence theorem will imply that this is a convergent sequence, and then using this recurrence relation, we will show that the limit of this sequence is exactly the root of this sequence, root of a. To establish that it's a bounded, let us first establish that the square of each term of the such sequence for n greater than or equal to 2 is greater than or equal to 2. So that 2 becomes the lower bound of this sequence. Now, as can be seen from this equation, and this is Sn plus 1 equals to 1/2 Sn plus a upon Sn, and this can be written as 2 multiplying to the left hand side, Sn plus 1 equals to, it is Sn square plus a upon Sn, a upon Sn. If I take Sn to the left hand side, I will get 2 times, I will get this equation, 2 times Sn plus 1 equals to Sn square plus a, and if I take all the terms to the one side, then I will get this equation, which is a quadratic equation in Sn, and Sn is a real number. So this establishes that this quadratic equation, which is x square minus twice Sn plus 1 x plus a equal to 0. This quadratic equation has, the Sn is a root of this quadratic equation, and since Sn is a real number, and so this means that this quadratic equation has real roots. And if a quadratic equation has real roots, that means the discriminant of that quadratic equation is positive. And what is the discriminant? Discriminant of this has to be, because in case of general quadratic equation ax square plus bx plus c equal to 0, discriminant is always given as b square minus 4ac. And you have this discriminant here to be 4a minus 4Sn square. And this discriminant being positive are greater than or equal to, must be positive. This equation has real roots, and so this is positive, may greater than or equal to 0, implies this Sn plus 1 square is greater than or equal to a for all n. And in particular, this means that Sn square is greater than or equal to a for all n greater than or equal to 2. So one thing is here. So actually we are establishing here that Sn square is greater than or equal to a, not from greater than or equal to 2. So this a becomes a lower bound for this Sn square. Let us see, we have to use this somewhere here, and to establish that this is a decreasing sequence. See, and to establish that this is a decreasing sequence, let's consider the difference of the nth term and its n plus 1th term. Sn is equal to this, and by definition, Sn plus 1 has to be 1/2 of Sn plus 1 a upon Sn. And if you simplify this equation, you get this 1/2 upon Sn square minus a upon Sn. And since we have established that this Sn square is greater than or equal to a, so this number is a positive number, and clearly this implies that Sn is greater than or equal to Sn plus 1, and this is true for every n greater than or equal to 2, and hence it implies that this sequence discarding S1 is a decreasing sequence, and it is bounded also by each term is bounded also. Since this is a decreasing sequence, we know that each term is a positive sequence, and a being the lower bound also, and it goes nowhere. S1 being its maximum, it goes nowhere. S2 being its maximum, it goes nowhere. It lies between two numbers, lower bound and upper bound, and it's decreasing, and by monotone convergence theorem it is a convergent sequence. And what is its limit? As reasoned, since Sn plus 1 gives you the corresponds to the tail of this sequence, and tail of a sequence and a sequence has the same limit, and we suppose that the limit of the sequence is S, and if we apply limit to this relation, recurrence relation, and also the algebraic properties of the limits, what we will get the limit of Sn plus 1 to be the same as equals to 1/2 of S plus A upon S, and solving this equation gives you S square equals to A, and this, since A being a positive number, implies that S is equal to root of A, and this actually gives you, establishes now that the sequence which is convergent and it converges to the root of number A. You can do it for any number, and you can start with any number to reach to the square root of a number. The following note tells you us that for the purpose of the calculation, we try to estimate how rapidly this sequence which we are defining converges to this root A, and the following inequalities can be utilized. And as can be seen, this inequality, if we calculate S1, if we start with S1, we can calculate this inequality. We will see how close we are to square root of A, and if you are far away, you calculate, put substitute n equals to 2, n equal to 3, up to 10, 11, 12, so on whatsoever. It depends upon the kind of S1 you choose, and then up to some decimal expansions we will be always able to approximate this root of A. Next example, we consider a sequence defined by this relation, En equals to 1 plus 1 by n whole power n, and we establish that this sequence is a convergent sequence, and again we will use here also a monotone convergence theorem. Let us first see what these terms are actually. En is equal to 1 plus 1 by n. If I use the binomial expansion, I will get this equals to j is sum from j equal to 0 to n, and this is the binomial coefficient, and 1 upon nj. Let me look at this binomial coefficient. This is nj. By definition, it is n factorial upon j factorial into n minus j factorial. I can write it as 1 upon j factorial separately. I can write n into n minus 1 up to n minus 1 j plus 1, and cancelling out this n minus j factorial, and out of this product n minus 1, now what I'm going to do, I'm going to take out n, and I'm going to take out n from each of these term in this product, and what I will be left with, I will be left 1 minus 1 by n and 1 minus 2 by n up to 1 minus j minus 1 by n. How many n's we are bringing out? We are bringing out j minus 1 n's and n itself, so that I will have this n to power j here. And so this binomial coefficient is equal to this term. And if you substitute this term here, and what you will have to cancel out, you will have this term, these terms nj and nj cancelled out, and so we will be left with, after expanding this sum, first two terms will be 1 1, and the second you will have j from equal to 2. I will be having 1 upon 2 factorial 1 minus 1 by 2. For j equal to 3, I will be having 1 upon 3 factorial 1 minus 1 by 2 up to 1 minus 2 by n. And for j equals to n, I will be having last term 1 by n factorial and product of these terms up to n minus 1. Likewise, I have to find the next term en plus 1, that can be seen from here, substituting n, substituting in place of n the n plus 1, but that term will contain one more term, of the one extra term from an en. Since en has how many terms? It has n plus 1 terms. The sum of this en has n plus 1 terms, and so en plus 1 will contain n plus 2 terms. So let us see, this is en plus 1. Now let us compare these two terms, en and en plus 1. Let us compare the first n plus 1 terms of both these terms. The first two terms of both these en plus 1 and en are same. Second, we don't have to compare these factorial part, 1 upon 2 factorial, it's same. I have to compare this number only. In en, the third term, the term there, if we have 1 upon n, this is in en, and en plus 1, we have in multiplication with 1 upon 2 factorial, I have this term 1 upon n plus 1. And clearly, which term is the larger? The term which has the denominator n plus 1 is the larger, clearly. So if we compare the first n plus 1 terms, then we see that the corresponding terms of this en plus 1 are larger than the corresponding terms of en, and in addition to that, this en plus 1 has one more extra term. So this means that en plus 1 is strictly larger than en. So with this, we've been able to establish that this sequence is increasing, and also it is clear that this E1 being equals to 2, and it is strictly smaller than E2, and so on up to. So 2 is a lower bound, and it's an increasing sequence. Now I have to establish that it is a bounded. It's increasing, okay, that's not an issue. Now we have to, it is bounded, and I have to establish its upper bound. How we are going to do this thing? Look at this. What we have, en is equal to 1 plus 1. I have 1 by 2 factorial, 1 minus 1 by n. Then I had 1 by 3 factorial, 1 minus 1 by n, 1 minus 2 upon n, so on. The last term in this has 1 upon n factorial, 1 minus 1 by n, so on. Product was 1 minus n minus 1 upon n. If you look at each term of in the sum of this en, except the first two terms, which are 1 and 1, in the second term, again not looking at this 1 upon 2 factorial, the other term, that is 1 minus 1 by n, this is less than 1. This term, this is less than 1. Similarly, in product with 1 by 3 factorial, the term which is there is less than 1, and in each term, this term is less than 1. So what it gives us this inequality, that this en is less than 1 plus 1 and 1 by 2. It will actually give us this following inequality. Let me write it separately. It will give us this en being less than 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial plus so on plus 1 by n factorial. But there is a relation between this power and the factorial, and this is valid. This can be established that 2 to power natural number p minus 1 is always less than p factorial, so that 1 upon p factorial is less than 1 upon 2 to power p minus 1. So this inequality further gets modified, and this gives us that this En is going to be less than 1 plus 1 by 2 factorial will be 1 by 2, 1 by 3 factorial will be 1 by 2 to power 3 minus 1, it is 4, 2 square, and plus so on plus final term is 2 to power n minus 1. 2 to power n minus 1. And now this is a geometric sum. After we let us look at the geometric sum of this is a geometric sum, and this geometric sum is 1 minus 1 by 2 to power n minus 1, and clearly the geometric sum is less than 1. Hence this total sum has to be less than 3. That gives us that this En is actually less than 3, and this is greater than or equal to 2. This is greater than or equal to 2, and hence this is a bounded sequence. It is convergent, which is increasing also, and the application of monotone convergence theorem, applying monotone convergence theorem, that this sequence is a convergent sequence. We cannot find its explicit limit E, but we are for sure that the limit of this sequence lies between 2 and 3. Its limit lies between 2 and 3, and this number that lies between 2 and 3, it is given a important name. This is called the Euler's number, and some of the first decimal numbers are it is 2.7182818284590. It has infinite decimal expansion, and this is also a important application of this